Well, as I said, to sketch a graph of function, you need to do few things. The first thing would be finding the domain of function, and as we know, the domain in general is all real numbers except for zeros of denominator and negatives of an even root. These are the exceptions of the domain. After you find the domain, you can go by checking the vertical asymptote, and the vertical asymptote can be found by evaluating limit of f of x as x approaching a from either left or right, and the values of a here will be, the possible values of a will be the zeros of denominator. If such a limit gives us either positive or negative infinity, this means that we will be having a vertical line passing through a, and that would be x equals a, will be a vertical asymptote. So we'll have a vertical asymptote, which is x equals a, and to check the horizontal asymptote, we need to evaluate limit f of x as x approaching either positive or negative infinity. If such a limit gives us a value L, then the line y equals L, the line y equals L this is the value of L, the line y equals L will be considered as horizontal asymptote. When you are done with vertical and horizontal asymptote, you can go through the first derivative test, and the first derivative test starts by finding the first derivative first, then finding the critical values, and the critical values are defined as where f of x is equal, f prime of x is either equal to 0 or when the function is not differentiable. And we know that the function will not be differentiable if it's either not continuous at such value or if it has a sharp turn, like the absolute value function, for example, a v shape. When you are done with finding derivative and finding critical values, third step will be by checking the sign of f prime on a number line. Let's say that we have a value c as a critical value. Then we need to check the sign of f prime by substituting values in f prime. If it gives us a positive value, then the function will be increasing till this point. If it gives us a negative value, then the function will be decreasing after that point. And from the sketch, we can figure out that here we will be having a maximum value. In case it was down, then we will be having a minimum value. Actually, maximum and minimum are called extreme values. Then you will find extrema from the sketch that you just found here. Okay. After that, you can go through finding f double prime to check for concavity by following same steps as for f prime. The only difference here will be the sign of f double prime. So let's say that we are having another value, let's say b as a critical value for f double prime. If you are checking the sign of f double prime, it gives you positive. This means the function will look like this, will be concaved up, and gives you negative, then the function will be concave down. And at b, where the function changed concavity, this will be called inflection point. So from the first derivative, we can get extreme values, maximum, minimum. From a second derivative, we may get inflection point. Of course, all of these are possible values. Critical values will give us possible values, but it's not a must. When we are done with all of these things, we can create a table of values as usual. The table of values will have x and f of x or y values. We prefer to use, of course, the extreme values, the maximum if we have, the minimum, the inflection, and any other extra values if we need. Sometimes we'll need extra values. That should be enough for us to make a sketch of a function. Now let's start with an example. Let's say we have f of x equals x cubed minus 3x squared. A normal polynomial function to make it easy at the beginning. So the domain of a function, since this is a polynomial, so we don't have zeros of denominator, we don't have radicals, which means domain in general will be all real numbers, or we can say open interval from negative infinity till infinity. Since it's not rational, so no denominators, which means no possible vertical asymptotes. And if you try to check for horizontal asymptote, of course, it's not rational again. And if you substitute infinity, that will give you an undetermined value, because infinity minus infinity will be undetermined. So no asymptotes, which means we'll jump immediately to the first derivative test. And we follow the steps. F prime of x will be equal to the power rule, addition and subtraction. So 3x squared minus 6x. This is the derivative. Now for the critical values, ends of the interval will be included, because the function is always undifferentiable or not differentiable at the end of the interval. And in this case, the ends are negative infinity and infinity. And then we have to find the roots. And the roots in this case, we need to check 3x squared minus 6x when it's equal to 0. That will give us, if we try to solve it, 3x as a common factor. So x minus 2 equals 0, 3x equals 0, so divide by 3x will be 0, or x minus 2 equals 0, so x will be equal to 2. So in this case, we have two critical values. We have to check the sign of f prime on the number line. So remember that you are checking the sign of f prime. So the values that we are going to choose, we are going to substitute them in f prime. So let's say I'm going to choose -1 in f prime. You can use this form. This is easy. -1 times 3, that's negative. -1 minus 2, that's negative. So negative times negative will give you a positive value. So this interval will be positive. Let's choose 1. This is positive times negative. So that will be negative. So this interval is negative. 3, that's positive, times the bracket, which is positive, so this part is positive. What does this mean? As we said, if f prime is positive, this means that the function is increasing. Negative means it's decreasing. Now it's positive, so increasing. Here, it's on the top, so we have a maximum value. Here in the bottom, so we have a minimum value. Now, what does all this mean? This means that f of x, remember that we are talking about the original function f of x, is increasing on which interval? Negative infinity till 0, union 2 till infinity. And f of x, again, will be decreasing on 0 to 2. And it doesn't make a difference actually when you are describing increasing and decreasing if the intervals are open or closed, because we are describing the behavior of the function. So it does increase from here to there. So if it's defined at 0 or 2 or not, That does not make a big difference. The function will still be increasing or decreasing. Now, at x equal 0, f of x has a relative or local maximum, which is, what's the value of f of x that is a maximum, which is f of the 0. And of course, we can evaluate f of 0 from our original function here in this place. So 0 minus 0, that will be 0. And of course, at x equals 2, we have a minimum value. Again, it's relative minimum. All extreme values are relative, actually, except if we have, if we are certain that this is the maximum, the top one, the biggest one, the greatest value, or the lowest value. In that case, we will call it absolute maximum or absolute minimum. So we have at x equals 2 relative minimum, which is f of 2, and we have to check that again. Remember, this is f of x, so we have to go to f of x again. So here it's 2 cubed, which is 8. 8 minus 4 times 3, that's 12. So 8 minus 12, that's negative 4. So this is negative 4. Now we are done with the first derivative test. We have to follow the second derivative in order to be able to identify intervals of concavity. So f w prime of x will be equal to, let's go back to f prime. F prime, here is f prime. So f w prime will be 2 times 3, 6x minus 6. So f w prime is 6x minus 6. We continue the same way, find criticals. So ends, roots, negative infinity and infinity roots. So 6x minus 6 equals 0, which means x will be equal 6 over 6, that's 1. Again, on a number line, 1, and we are checking the sign of f double prime in this case. So choose a value less than 1, let's say 0. 0 minus 6, that's negative. A value greater than 1, let's say 2. 12 minus 6, that's positive. In the negative interval, the function will be concave down. In the positive interval, the function will be concaved up. Now, since the function changed concavity at 1, then the point at 1 will be called inflection point, and it should be written as a point. So 1 and f of 1 is an inflection point. We need to evaluate that, of course. 1, f of 1, again, we're talking about the original function. All what we are doing is to graph the original function. So 1 minus 3, that's negative 2. Now we can create a table with what we found. X values, y values, or f of x values. The values that we have are 0, 1, and 2. These are what we have. The one here, it's negative 2. At 0, what did we get? At 0, we got 0. At 2, we got negative 4. So here we have 0 and negative 4. We can choose extra values. If you want something before 0, something after 2, we can still add points, and that's optional in case we need more. So I will use negative 1 and I will use 3 here. So when x equals negative 1, when x equals negative 1, we'll be having negative 1 minus 3, that's negative 4. When x is equal to 3, we'll be having, where is it? 27 minus 9 times 3, 27. So 27 minus 27, that's 0 again. Now, let's see how would that affect our graph. Okay, now what do we have? Now we know that our function is increasing till 0, decreasing till 2, then increase, and we know the concavity intervals, and of course we have our points that we have just found. Let's plot these and try to translate all what we found on the graph. First point is 0, 0, 1, negative 2. Let's plot these. 0, 0, 1 and negative 2, 2 and negative 4, 3 and 0, 1 with negative 4. That's what we found. Okay, now let's try to translate everything. So the function will be increasing up to 0, which means it will pass by these points and it will be increasing, and then it is decreasing from 0 to 2, so it will pass by the points, decrease till 2, then it's increasing after 2 till infinity, so it will go like this till infinity. Now, if you notice, I didn't use the concavity yet, so now let's put everything together. The function was concave down till 1, which means it will pass by all of these points, but it will be concave down till 1. So it should come with a curve to show the concavity, concave down, and then it's concaved up after 1, so it will continue same thing, but will be concaved up. So it will continue decreasing, but will be having the shape of concavity up, and this is our final shape. Of course, will continue till infinity and continue till infinity from the other side. And that's it. We can apply this into all functions. Our next example, inshallah, will be about rational functions. That's something that includes vertical and horizontal asymptotes. And good luck.